Good evening and welcome to the Falco deep dive session for KubeCon. Tonight we're going to talk about runtime security with Falco in Userspace. So how to use Falco in those environments where no access is allowed to the kernel of the operating system, which is where tools like Falco typically get their information from. The talk is going to cover a little bit of Falco at a high level to give a tiny bit of context, then deep dive into the Falco collection architecture, give an overview of the options that we have to collect data for Falco in Userspace when kernel access is not available. Talk about a tool called Sysdig, which puts these theories in practice, and then leave some space for questions. First of all, my name is Degioanni. I am the founder and CTO of a company called Sysdig, which provides tools for security and visibility for cloud-native environments based on Kubernetes. I am also one of the original creators of Falco in 2016. I'm still an active contributor to the tool. And before Falco, I spent a lot of time in open source and networking. In particular, I was one of the original contributors to wireshark, the open source packet network analyzer. You find me on Twitter at @LorisDegio. All right, let's talk a little bit about Falco. Falco is a runtime security engine for containers and for Kubernetes. You use Falco to create rules that will notify you when you're triggered about unwanted activity in your containerized environment. For example, when somebody is touching a sensitive file, exfiltrating data, establishing connections that are unwanted, executing commands that are strange, and stuff like that. Falco leverages the kernel of the operating system to collect information, and in particular is based on some technologies for collecting data. One of them is called eBPF, and stands for Enhanced Berkeley Filter, and we'll talk a little bit about it later, but allows Falco to essentially collect system calls from the operating system. Very importantly, Falco is designed to be modular and consumable. So Falco is a component that we designed to be very tightly embedded in the cloud-native ecosystem and in the cloud-native stack of tools, and is designed to interact and interface with these tools to be part, essentially, of the pipeline. Falco uses the kernel of the operating system, in particular Linux, typically, as the source of truth, and takes this information and enriches it with metadata coming from the orchestrator, from Kubernetes, for example. Service, labels, annotations, all of this kind of stuff is consumed by Falco to make it possible to offer a view that is not only container-centric, but it's also service and user and application-centric, which is very important when doing runtime alerting and runtime protection of your infrastructures, because you're typically much more interested in what service is showing an anomalous behavior rather than just getting a container ID or something like that. Falco is a CNCF project, very important for us. We started Falco in 2016. We got accepted by CNCF as a sandbox project at the end of 2018. And around 6 months ago, in December of 2019, we were promoted to incubation. It's a big focus of us to make sure that Falco is a project that has a broad audience, but in a way that is completely open. It's community oriented, and it's it's driven by the guidelines at the core of CNCF. Let's go a little bit into architecture. At the high level, the Falco architecture is relatively simple. There are inputs, there are rules, there's an engine, and there are outputs. So inputs, of course, can be, as I was mentioning, kernel events in the form of system calls, but also container metadata, Kubernetes audit events, Kubernetes metadata information, and so on. Rules allow you to specify essentially conditions on these inputs, and are evaluated at the edge by Falco engines that are running on every machine. And they provide outputs that can be, can go to syslog, can go to standard output, can go to gRPC or webhooks, can go, for example, there's an integration for Prometheus, so there's a bunch of ways essentially to consume Falco outputs. Most of the people tend to send the outputs coming from Falco through syslog or through some other mechanism to a SIM tool that then can collect all of this kind of stuff in a centralized place. And Falco, of course, puts a lot of richness in these events and a lot of context. And then from the SIM tool, you can essentially create dashboards or investigate or alert or do whatever you want. Some rule examples. As you can see, Falco is designed with a syntax that has the goal of being as lean and as simple as possible. So maybe compared to other security Kubernetes tools, like for example OPA, Falco is a less expressive syntax, but also a very simple syntax that allows you to create sophisticated stuff with one-liners that are pretty easy to grasp and pretty easy to manage and create new ones. For example, a shell is running a container, as you can see, is a condition that says container ID different than host. So we're actually inside the container, and there's a process called bash. Overwrite system binaries. We have a write operation in one of these directories. Container namespace change. So this rule, for example, is trying to detect a container trying to escape its namespace, its jail. And as you can see in this one, we look at the setns system call, and so on. Rules can become more and more sophisticated, but at the basic, they trying to be simple, expressive, and powerful at the same time. Okay, now that we've seen what kind of rules we can express and how it works, let's look at how Falco collects the data, because the whole value and richness of a tool like Falco and the ability to run at runtime and inform you of granular changes and actions in your infrastructure depend on the ability to collect the best data. In particular, Falco uses the kernel of the operating system to collect system calls. So here in this diagram, we have a simplified diagram of a machine. In this slide, we have a simplified diagram of a machine with the kernel of the operating system, and we have 3 containers running on this machine with 3 different container runtimes. You deploy Falco by running another container on the machine, only one new container. You typically do this through a daemon set, for example, in Kubernetes, by telling Kubernetes, on each of my hosts, I want a Falco container, only one. If it goes down, bring it back again. You click enter in kubectl, and essentially you've pushed Falco everywhere. When Falco starts on the machine, it detects the version of the operating system, and it deploys instrumentation at the edge between the containers and the operating system itself. This is important because Falco is not based, the traditional instrumentation for Falco is not based on sidecars, is not based on installing something inside the container, but it can achieve this visibility by just running one separate container and by instrumenting the kernel. This is very key in terms of easiness to deploy and scalability. Once this is deployed in the kernel of the operating system, typically under the form of an eBPF module, Falco is able to collect every single system call. So let's first talk a little bit about eBPF. As I was saying before, eBPF stands for Enhanced Berkeley Packet Filter, and it's essentially a virtual machine that runs in the kernel of the operating system and allows you to inject scripts in the operating system to do a bunch of different things. Falco uses it to collect system calls, and eBPF makes it possible to do that in a way that is at the same time extremely efficient, because this code is just-in-time compiled and heavily optimized, but at the same time safe. Safe because eBPF is validated for stability reasons. Essentially, eBPF can only do a minimal set of things inside the kernel, and what it does is validated before the program is just-in-time compiled, so that you don't crash. You're guaranteed not to crash the kernel unless there are bugs in the kernel when you're running an eBPF script, and at the same time safe from the security point of view, because the scripts are sort of sandboxed inside the kernel. So it's a beautiful way to essentially extend and include functionality in the kernel that allows a tool like Falco to operate. At that point, the eBPF scripts allow Falco to capture system calls. As I was saying, system calls are anything, reading or writing to disk, opening files, establishing network connections or receiving network connections as servers, inter-process communication, executing commands. This is all system calls. So on a really super granular way, Falco is able to collect all of this information and give you essentially notifications if something goes wrong. Kernel-based instrumentation is very powerful, and the reason why we chose it as the original way to instrument Falco is because it's accurate, it's in the kernel, so you don't really bypass it, and it really collects everything. It's extremely efficient, so it slows down minimally the target containers and the target applications. At the same time, it's scalable because you only need to deploy one thing, and then you can have one container running on the machine or 1,000 containers running on the machine. The instrumentation point is always one, while when you have sidecars, essentially the overhead of the instrumentation tends to be linear with the number of containers that you're running. The problem with kernel-based instrumentation is there are some places where kernel instrumentation is not available anymore. I mentioned in Fargate, for example. So Falco needs access to the kernel. The collection system that I described requires kernel access, but there are places like, for example, Fargate in AWS or Microsoft Hyper-V containers where this access is not available anymore because essentially the same machine could host multiple containers from multiple users. So it's not safe to give one of these users access to the kernel. This could create issues for the other users that are in a multi-tenant environment sharing the same machine. So how can we address this? We need to find a solution that collects the data with the same granularity, but that does not access the kernel of the operating system. There are a couple of ways. One that typically comes to mind when doing this kind of stuff is the so-called LD PRELOAD. LD PRELOAD means being able to tell the operating system through an environment variable to get system libraries from a different place. So instead of getting them from inside the container, it's possible essentially to map an external volume and then replace some system libraries. For example, the glibc, the C library of the container. C libraries, the C library is the gate between any application and the kernel of the operating system. So when you issue a system call, typically you go through libc. So if we replace libc in one of your containers, then we're able to install some instrumentation that can send the data to Falco. LD PRELOAD has the advantage of being efficient, pretty easy to implement, but has the huge disadvantage that it requires essentially replacement of dynamic libraries in an application, which by itself is a little bit dirty. But even more importantly, it's limited because it doesn't support whole classes of applications that just don't use libc and they don't link dynamic libraries. C statically linked programs have this feature. They use dynamic libraries. And Go is another example. Go has been designed to generate, at least on Linux, completely static binaries and doesn't really use libc. So an LD PRELOAD approach would not support Go programs, which is a pretty massive limitation in cloud native. Another approach is using Ptrace. Ptrace is a functionality in the Linux kernel that allows deploying essentially something inside the container that can essentially detect every single system call by going and getting access to the monitored application. Ptrace is what's at the base of tools like GDB or Strace. So just by looking at what GDB can do, you can get a hint of what Ptrace can do. It can freeze a target process, it can install breakpoints, it can inspect the memory of the target process. It can also see every single system call and the arguments of the system call. So by leveraging Ptrace, it's possible to essentially create a tool, I call it PD here, that can collect the system calls and send them to Falco. Benefits of Ptrace are it's accurate because you still go through the kernel. So I used to say the kernel never lies because it's hard to bypass something that is collected at the kernel level. At the same time, Ptrace has a couple of limitations. One is performance, and the other one is that historically it's disabled on some of these platforms. For example, you cannot use Ptrace in Fargate. This is something that is changed because very recently, a few weeks ago, Amazon has announced the Fargate engine 1.4, and Amazon has added this capsys Ptrace by working with people like the Falco maintainers, so that there could be a path essentially to have a system call collection at user level on a platform like, for example, Fargate, which is pretty new and pretty mind-blowing if you think about that. Let's take a look. So I'm switching to my AWS console, and as you can see here, I have a couple of tasks, and I have one that is called Falco Trace SSH. So let's go inside it, and let's gather the public IP. This is essentially a container that is running Ubuntu. And let me SSH into it. And now, wrong password. And now we're inside the container. This container has been instrumented with the technique that I just described. So we have pdig running inside this container using Ptrace to collect information. So I can do some simulated malicious activity here, like I can change a system binary /bin /cat. And now I'm going into my console. Actually, let me refresh. And as you can see, sure enough, I've been notified that the system binary has been changed inside this container. So we get essentially granular runtime system call level visibility through Falco on Fargate, thanks to Ptrace based instrumentation based on pdig. One more thing that I want to talk about is performance. So as I was saying, the issue with Ptrace is that it tends to be relatively slow, because every time there's a system call, every time the application talks to the kernel of the operating system, the system call needs to go up and go back to Userspace and be delivered essentially to a separate process running inside the machine. This process, by the way, needs to be essentially loaded in the container. In my demo, I loaded it as the entry point of the container, so that then everything inside the container would be captured essentially. And doing that creates a little bit of an overhead. There are things that can be done to accelerate this, because otherwise, without optimizations, Ptrace would just be, as a technique, too slow to work effectively in production on your containers. So we do multiple things to make this faster. One example is the use of seccomp BPF. When Ptrace has been enabled, for example, on Fargate, in the environment where I give the demo. Another thing that was enabled by Amazon was seccomp BPF, which allows essentially to inject little simple BPF scripts that can selectively capture only specific system calls. For example, Falco needs to know when a file is open or when a connection is established, but Falco doesn't currently look at the payloads for performance reasons. So through seccomp, we can selectively capture and do this path, this trajectory, only for some system calls and not other system calls. And the result is that we can greatly, essentially, minimize the number of system calls that are captured by PDIG and delivered to Falco. And by doing that, we can be much more efficient in the capture. There are also other optimizations that we're doing, but those go a little bit deeper and might be the subject of a future KubeCon talk. For the moment, I'm just giving you a few links if you want to play with this. In particular, everything about Falco is on falco.org, and anything that I showed on this demo is already available for the community under the Falco organization, and can be essentially downloaded from GitHub. This is where you download and install Falco from GitHub, and this is where you find PDIG on GitHub. So please, go ahead, have fun with this, and of course, reach out to the community if you need any help with this. But let me maybe stop here, and let me open this up for questions. And thank you very much for the moment.
Okay, really thanks for the great talk from Loris. And here is the Q&A session. Loris, you can take a look at the Q&A tab in Zoom and answer any questions you want to answer. Thank you.
I believe there are no questions for the moment, right?
Yes. Yes. Just wait a second. Yes. Oh, here we go. Yes.
Darcy, are there any good tools which work with Falco for visualizations and easy configuration? So yes, one of the goals of Falco as a project, of course, is integrating as best as possible into the rest of the ecosystem, and of course into pipelines to collect these events, transport them, and so on. So if you go either to the Falco website or to the Falco blog, which you find from the website as well, you will find several reference architectures to, for example, integrate Falco with Elastic for message collection, or with event pipelines on AWS or Lambda, or stuff like that. So yes, there are many. Another one, for example, that I can mention is Prometheus. We have exporters for Falco that can convert Falco alerts into Prometheus. So then you can, Falco metrics that go into Prometheus, and then you can use any Grafana or any other tool to visualize essentially the reports and the statistics about what you receive. So again, go to the website, go to the blog, and you will find a bunch of information. What is your opinion on having a Kubernetes distribution that is secure by default, with opinionated configurations and tools integrated? you are really talking to somebody here that has this strong conviction. It's the Falco community does a bunch of work just with distributions in order to have, yes, this kind of functionality embedded into just Kubernetes when you get it. For sure, Kubernetes itself is making a lot of progress in terms of just getting better included from the security point of view, but there's definitely space. I see, especially the runtime security that Falco does to be, it would be a great benefit if it's just integrated by default into the distro, and then maybe also integrated into mechanisms like admission controllers and so on to create a positive feedback loop to protect and self-heal essentially your infrastructure. One thing that, for example, I can mention that we have announced recently is the integration between Falco and OpenShift through the Red Hat ACM 2.0. So Red Hat now has an operator that makes it possible to essentially with a single click to just have Falco deployed in your cluster and configured essentially by default when you bring your cluster up. This is hopefully just the beginning, and we're seeing, definitely a lot of potential into just embedding Falco by default and having a curated default set of rules that you have for runtime protection.
Yeah, I think Falco right now is the incubation project, right? So when it goes to the graduated project in CNCF, it might be can include it in the Kubernetes distribution, right?
Absolutely. It's very much so, and very much a goal of ours. For sure, to go into graduation, one of the criteria that the TOC looks is tight integration with the rest of the CNCF ecosystem, and Kubernetes here is definitely the tool that Falco wants to integrate with.
Yeah. Okay. Thanks for the great talk from Loris. Thank you. And our next talk will start at 9:30. So we will play the warm-up video right now. Welcome. Be patient and welcome back later. Thank you.